So today we're going to be looking at minerals. Now this presentation is going to be a little bit different than the ones we've had in the past in that you're not going to have a quiz at the end of this particular video. What you're going to do is you're going to take notes in your notebook and you'll have an assessment a little bit later on. What you should do is outline 2 pages in your notebook like this. On one side, write a title of minerals video lecture so you know this is the minerals material so you can find it later. And you're going to have a vocabulary page and you're going to have a concept questions page. As you go through the presentation, any word that you see red and in bold, you know that is a vocabulary term which should be written and defined on that left-hand page. The concept questions on the right. There is no handout for you and there's no fill-in-the-blank page to guide you through this, but the concept questions are going to be numbered and they're going to be quite obvious as you go through the presentation. Yes, you need to write the question because the answer without knowing what the question is isn't going to do you any good when we get to a notes quiz. First of all, definition of what a mineral is, and you'll notice that this is a red bold-faced word, so that's something we need to put on the vocabulary side of our notebook. And the wording on this is very particular. I know it's long and it's kind of wordy, but to get the definition of a mineral, we need all these components. And if you do a Wikipedia search or Google search, you'll find a lot longer, more confusing definition of what a mineral is. So I've broken this down as short and as sweet and as precise as possible. And you see it there. It's a naturally occurring inorganic solid with an orderly crystal structure and a definite chemical composition. So there's our definition. Our first concept question, you're going to write this on the opposite page. Number 1, what are the characteristics to be a mineral? And they were just listed in that definition, but we're going to examine these individually. First of all, it has to be naturally occurring. In other words, it cannot be man-made. Simple enough. It's got to be found in nature on its own. The second is it must be a solid, so no liquids or gases. This doesn't really need much explanation because you know what solids are versus liquids and gases. It must have an orderly crystal structure. Now let's explain what that means. All that means to you and me is that the mineral, the atoms that make up the mineral, are put together in a certain pattern that is always the same. It's not put together one way one time and another way another, and it's not haphazard. The atoms that make up a mineral have to be put together in a specific pattern to make it that mineral. If they're put together differently in a different pattern, that means it's a different mineral. It has to have a definite composition. Now, what does this mean? Well, definite means it's set. It is definitely something. A composition is what is it made out of. This basically is simply stated means that it has a certain recipe. So think about water. And water is not a mineral, but you'll get the idea. You know that water is H2O. Water is never H3O that one time in a billion. It is H2O and always H2O. That's the same thing with minerals. They always have the same recipe that never changes. If you change the recipe, now you've changed to a different mineral. Finally, has to be inorganic. Inorganic means non-living. And this is a little tricky because not only is it not living now, it means it was not living material at one time. So a dinosaur bone that we dig up out of the ground is not a mineral because it came from something that was alive at one time. So question number 2, why are water, plastics, and coal not considered minerals? Well, water's a tricky one. And actually with water, we could technically say that water in a glacier is a mineral because it is a solid, it is naturally occurring, has a definite chemical composition, yada, yada, yada. It meets the requirements. But generally, we think of water in its liquid state, definitely not a mineral because it is not a solid. Why are plastics not minerals? Well, plastics are man-made. They also don't have a orderly crystal structure. They're not put together the same way every time, and you know this, that plastics can be many different compositions, and they're not true solids either. They're a lot more like liquids. This here is coal. Coal looks like a mineral. I mean, it's solid, it has an orderly appearance, has a definite composition. The trick with coal is coal comes from formerly living materials, whether it's old dinosaurs that have decomposed in the ground or plants. So coal is not a mineral because it comes from a living material. Now, granite. Granite's a rock we've looked at. Granite is a rock. It is not a mineral. And the reason this is because that granite doesn't always have the same competition. All of these samples here are granite, and you can see some of them look very different from the other. Well, because granite is a mixture of a bunch of different stuff, and the mixture can change one time to the other. Well, minerals can't do that. Minerals always have the same composition. They have to in order to be classified as a mineral. So granite, not a mineral. Question number 4, how many minerals are there? There's about 3,800 different minerals out there. Now, where do these minerals come from? They're natural, so they were formed somehow. Well, how did these 3,800 different things get made? Out of all the minerals, there's only about 4 different methods, 4 different processes by which we can actually form minerals. Concept question number 5 is going to be list and describe these 4 ways. So write the question out clearly, and then underneath this question, we're going to describe each one of the 4. First of all, method number 1 is called crystallization of magma. You know what magma is? It's molten rock that comes up under the ground. Crystallization basically means that it is cooling and hardening. So different materials cool and settle or collect at different times. So that's why you get, even in the same rock, you'll get, oh, this olivine, it starts to cool at 1200 degrees. So it starts to clump first. At 900, the pyroxene starts to clump together. Now, the olivine has already formed. So now we've got 2 different clumps of minerals. And at 600, now we get the feldspar that starts to clump together. So now we've got 3 different minerals that all came from the same magma, and they started to clump together because they cooled at different rates. Here you can actually see it. Here's a nice big dark basaltic rock, and you can see here there's a little chunk of a green crystal in there. That's a mineral. That's some of the stuff in the magma that started to cool together and then clump together. In the in the rock, granite, you can actually see there's some dark minerals, some black minerals, there's some white minerals, and then there's some tan minerals. The minerals form because the stuff starts to clump together as the magma or lava cools. Precipitation is the second method, and we're not talking about water that falls from the sky. We're talking about minerals that come out of water. The residue that you get from hard water is an example of how you get minerals formed by precipitation. The minerals are in the water goes away, some of the minerals are left behind. Here you can see that when water moves through rocks, well, it finds little holes in the rocks, and the water keeps moving through the rock, but it drops some of the minerals behind, and that's what's called mineralization. You get precipitation, you get minerals being made in the little holes in open spaces in rocks where the water moves through. Stalagmites and stalactites, if you've ever been in a cave or you're familiar with these, all these are mineral formations. What happens is water starts to seep through the ground, and then we get this little drop of water here, and then it falls to the floor of the cave. Well, when the water drops, it leaves a little bit of minerals behind, and over time we wind up with a bunch of a pile of minerals, and that's a stalactite. Well, when the water hits the ground, the minerals also start to pile up, and you get a stalagmite. Halite, which is a very common mineral that we put on our food. It's what we call table salt. It is formed specifically by precipitation. You have salt water, and if you evaporate off the water, you're left with salt. Well, we know there's a lot of salt in salt water. So this is how halite, the salt that we put on our food, was formed. Works like this. Now, years ago, when there was a lot more water in the oceans, our shallow places were more covered in ocean water. So we had salt in this area here. Well, ocean levels have gone down, and now the water in here evaporated. Well, the water evaporated, but the salt stayed behind. So now if you go in this area right here and dig in the ground, you're going to find a big collection of salt under the ground. That's actually how we get most of our salt, is we dig mines. We find places where there was a low point that salt water had collected but then evaporated, and it left the salt behind. Here's the Kansas Underground Salt Museum. You go down about, I think it's like 700 feet underneath the ground, and they are digging out big, huge chunks of salt from the ground. That mineral of halite, what we call table salt, was formed when a bunch of salt water evaporated and left the salt behind. Once again, minerals forming by precipitation. The third method by which minerals can form is what we call hydrothermal alteration. Hydro meaning water, thermal meaning hot, alteration means to change. So this is when we get hot spring water that's moving through rocks, and it causes the rock to change and form new minerals. A hydrothermal solution is part of this equation. A hydrothermal solution is a hot mixture of water. Think about it as like hot spring water that has a lot of dissolved minerals in it. And you already knew that to be true. So when the hot water comes to the ground, the minerals get dropped off, especially as they react with the other rocks, you get minerals formed. Here's an example where they tapped a hot spring. I showed you this earlier in the year, and the hot spring water came out and had so much minerals with them that they just started to pile up. Here you can actually see this nice dark black lava rock in Iceland. But what's happening is hot water is coming up out of the ground from the volcano, and it is hydrothermally altering this black rock. You can see this rock now is not the same. It has been changed into a new mineral by the action of the hot water. Now, as that hot water moves up through the ground, it finds its way through little cracks in the rocks, and you get what's called a vein. So the hot water was coming up through this rock, and it found its way through there, and then it went this way, and it went that way. That was the space that it could find in the rock. And the minerals that were in the hot water get dropped in those little spaces in the rock. So this is why rocks have veins in them. They're veins of minerals where the hot water was able to force its way through and then drop the minerals. A geode. Geode is a special type of rock, and what it is a hollow rock where hot water got in there. Well, the hot water then got in there and cooled, and the minerals started to cool, and they started to crystallize. So a geode is a hollow rock where minerals were allowed to form in that open space. Here you can see one just in the side of a random rock. You can see there's the open space, and you can see the minerals got in there and started to crystallize. The fourth method is what we call changes in temperatures and pressure. So I've got some rock underneath the ground. If I squeeze it hard enough, I'm going to rearrange the atoms, and I put them in a new order. Remember, minerals are defined by their particular order. So if I change the order of one mineral because I heat it or I push on it, I can then change it into something new, a different mineral. So this is the fourth method by which minerals can form. Is I take an old mineral and I heat it and squeeze it, and I force it to rearrange itself into something new. The best example I can give you of that is carbon, graphite, and diamond. These are all minerals, but they look very different. Amorphous carbon here is just kind of a loose collection of carbon atoms. If they get squeezed together loosely, they'll become graphite. But if you make the heat and pressure high enough, you'll get diamond. Now, all three of these are just carbon. But you know diamond and graphite are very different than one another. What makes diamond a different mineral than graphite is that it was put under a great amount of heat and pressure, which changed it from carbon into diamond. So question number 6, what common mineral is formed by precipitation? That would be halite or table salt. And one of the ways in which they make table salt is they take some ground that has a lot of salt in it, and they mix it with water, set the water out in the sun, the water will evaporate, and what's left behind is salt. Now, the characteristics of minerals, because we have about 3,800 different ones, we have to have a way in which we can identify one mineral versus another, and there are some very specific characteristics that we use to describe minerals. The first is color. Now, I don't have to define what color is. You know what purple versus blue versus red is. But what causes different mineral colors? Because the atoms are put together in a certain pattern, as they get put together, whether it's by heat or pressure or precipitation or whatever, you can get other stuff that gets trapped in there with the mineral as it's being put together. And that can change how it reflects light, and that is what color is. Here's a very common mineral, quartz. We have rose quartz, which is pink, clear quartz, obviously, which is clear white, and with smoky quartz, which is kind of a darker color. But yet, we can also have yellow quartz, we can have milky quartz, and we can have purple quartz. So all of these are all the same mineral, yet they had about 6 different colors. The same is true with beryl. The same mineral can have lots of different colors, even though it is exactly the same mineral. I want you to think about it this way. Think about different colors of cotton t-shirts. Now, they're all the same thing. They're all cotton t-shirts. But what you did differently was you trapped a certain dye in the cotton. Well, that didn't change the fact that it was a cotton t-shirt, it just changed the color of the shirt. And that's how you can have a mineral like quartz that can have many different colors. So, question number 8, how useful is color for identifying a mineral? Not much at all, because there are not 3,800 distinctly different colors. So each mineral cannot have its own color. And you can see these two, they're both a very similar color of red. We can't use red or the color alone to identify what a mineral is. Streak. This is a red bold-faced word, so we're going to write streak on our vocabulary side. Streak is the color of the mineral in its powdered form, which is sometimes very different than what it looks like as a solid. You'll notice this one here, this looks like kind of like a black mineral, yet when you rub it on a streak plate, it leaves a brown streak. This one here looks, I don't know, kind of golden or coppery, shiny, but yet when you rub it on the streak plate, it comes out gray. So this is a characteristic of minerals that is helpful to identify one mineral versus another. Well, we do that by using what's called a streak plate, and we will use these in the lab shortly. You take a mineral, and notice these are all kind of dark black minerals. This one over here had no streak at all. This one left a red one, this one left a brown one, this one left a kind of grayish silver one, and I think this one left a white one that you can't even see on the white streak plate. So we use a streak plate to scratch the minerals into their powdered form, which can help me identify one versus another. Now, luster. And I think I just skipped the luster is a term that we're going to put on our vocabulary slide, or side of the page. Luster is how a mineral reflects light. That's the definition we need. Our question number 9 is we're going to list and describe the different words that we use to describe what the luster of a metallic luster means it's shiny like metal. You know what metals look like. They're shiny, they're reflective, they reflect light. So a metallic luster means it looks like a metal. Glassy or vitreous luster means it's clear like glass. Light will go through it. Once again, we're listing these under our question where we're describing the types of luster and describing so that we know kind of what it looks like, so that when I pick up a mineral sample in my lab next week, I'll be able to say, oh, this one's glassy, this one's metallic. Adamantine. Adamantine is diamond-like. Means it's shiny, it's brilliant. Most of your jewelry minerals, your gemstones, have adamantine luster. That's why we use them for jewelry. We like shiny things like diamonds. Waxy. You know what candle wax looks like. It means it's not really shiny, but it has kind of it is what it says it is. It has kind of a looks like candle wax. Now, pearly or milky is a little bit different. It has a little bit more of a shine to it than a waxy luster. When you hold it up in the light, it's going to seem to be a little bit shinier than something that is waxy. Earthy. Earthy is kind of a generic term. It's a term that we use when basically nothing else applies. It's dull, it's earthy, it's plain. There's nothing special about it. And you can see here we got 3 different minerals that look very different, but they don't fall into any of the other categories, so we call these earthy. Crystal form, another bold-faced word, red bold word. Crystal form is simply how are the atoms put together. And this gives some minerals their very distinctive shape. Some minerals will go into cubic shape. Some of them will make little points. Some of them will make kind of long straws. This is indicative of how the minerals are put together, how their atoms lock together and make certain shapes. Cleavage. Now this is a term that is unique strictly to minerals, and this is how do minerals break. If minerals break into flat surfaces, they are said to show cleavage. And the way this happens is you've got a bunch of atoms stuck together, and sometimes the atoms stick strongly to each other and sometimes they don't. In this case here, the atoms don't stick to each other strong this way, but they do stick strong to each other this way. So if we take the mineral and we whack it with a hammer, you wind up with flat sides. Something like this. All of these minerals here were not cut. They naturally break into flat sides, and this is called cleavage, and it has to do with how the atoms are being held together. You can see this here is mica that we'll take out when we do our mineral lab, and you can pry it apart like sheets of a piece of paper. The very definite cleavage. This one right here, nobody cut that way. When somebody hit it with a hammer, just like this one down here and this one down here, it tends to break with flat sides to it. That's called cleavage. Now, cleavage can happen a couple different ways. It can happen in one direction, meaning there's only one side that's always flat. Like say this one, it always breaks into flat sheets this way. You can have cleavage in two directions. In other words, when you hit it with a hammer, you wind up with two flat sides, or you wind up with three flat sides, like a cube. You can wind up with three flat sides and it doesn't make a cube, it makes a slanted cube. Now all of these characteristics are going to help us identify one mineral versus another. Does it have cleavage? Yes or no? And with its cleavage, is it one, two, or three sides? And is it a cube or not a cube? Fracture. Some minerals, when you hit them with a hammer, they don't make flat sides. They don't exhibit cleavage. If a mineral is broken and it is entirely jagged, if it does not show flat sides, it is said to show fracture. Fracture is when minerals don't break into flat sides. Conchoidal fracture is a special type of fracture, and that will help us identify some minerals because what happens, they get these little kind of swirly round shapes in there. Conchoidal fracture is when it breaks and it has a slight circular pattern, which is a conchoidal shape. Hardness. Hardness is kind of simple. This is what it says it is. It's the resistance, how hard the mineral is, it is its resistance to scratching. Can you scratch it? Is it soft or is it hard? Is it tough or not? And the way this works is we take a bunch of different minerals and we compare them to another. And we do that using what's called the Mohs hardness scale. The Mohs hardness scale is a way to compare one mineral to another based on its hardness. Minerals are rated from 1 to 10. We take a soft mineral and we call it a 1. We take diamond and we call it a 10. And we then try to compare them to another. A harder mineral will scratch a softer mineral. So if I take 10 known minerals, I have a scale that I can use to rate any other mineral. Here's what it looks like. Diamond. Diamond is the hardest mineral. It is a 10. Nothing will scratch diamond. Diamond will scratch conundrum because conundrum is not as hard as diamond. Talc is very soft. You could scratch it easily with your fingernail. You could probably crush it in between your fingers. And you can see quartz is a 7. So a diamond would scratch quartz because diamond is the hardest, but quartz would scratch apatite. Density. Density is a term you've had in physical science and just means how tightly together the mineral's atoms are put together. Some minerals have their atoms really, really squeezed together tightly. Others don't. Now, this is going to be on a separate page of your notebook. You're going to make a chart like this of the common mineral groups. So you'll have to pause the video and copy this information down, maybe turn the page sideways so that you can fit this more clearly and easily onto one page.